I'm Seungmin, who is pursuing PhD degree in SNU, and in this talk, I'm going to talk about one of my recent works, CPR, Classifier-Projection Regularization for Continual Learning. This work was conducted with my great colleague when I was in Harvard as a visiting PhD student, and it is collaborative work with Xixiang Xu, Taebaek Hwang, Professor Flavio Carmon, and Professor Taeson Moon, who is my advisor. And this work is presented at ICLR 2021. Before the start talk, I want to have a short time to introduce myself. As I already introduced, I'm Seungmin, and my advisor is Professor Taeson Moon. During my journey for getting PhD degree, I have been focused on the topic of continual learning, unsupervised image denoising with neural networks. Especially, I'm more focused on continual learning these days. I'm conducting my continual research divided into two categories, and I could have a chance to publish several papers because of my great colleagues. The first category is core continual learning research. In this topic, I have tried to propose a generally applicable continual method for neural networks. The second category is applied continual learning research, and in this topic, I have proposed to more domain-specific continual learning methods, such as for semantic segmentation and natural language processing. Among them, today I will briefly introduce CPR presented in last year ICR. Let's start from the introduction to know what is continual learning and what is the goal of continual learning. These days, neural net-based method shows impressive results in various domains. However, a training method of neural net is not effective than human. For example, the current best solution to train a superior neural net model is to gather all training data set and train the model with them. On the other hand, human can effectively learn from a sequence of tasks with little forgetting than neural networks. In this regard, the goal of continual learning for neural networks to devise an algorithm to make the neural net model effectively learn from a sequence of tasks without forgetting, more like a human. So in this setting, so similar can mean kinds of representation or average accuracy, but in research topic, average accuracy is generally used for the metric. The research for continual learning with neural networks has been mainly conducted in the classification task. In classification, a set of classes is considered as the task, and the goal of continual learning in classification is that a model should learn newly arriving classes without catastrophic forgetting on the previous classes. And it is generally known that the main challenge of continual learning is the dilemma between plasticity, which is learning well new tasks, and stability, which is overcoming catastrophic forgetting on previous tasks. In recent years, many of the works on continual learning are proposed, and the continual learning algorithm can be categorized into the three subtopics. The first category is example-based continual learning, and in this setting, using a tiny example memory for saving previous task dataset is allowed. So the goal of method is to devise a way to use this memory more effectively during continual learning. The second category is dynamic network architecture-based method. To overcome catastrophic forgetting, these kinds of method dynamically expands a model when it's required. The final category is about regularization-based continual learning, which is the mainly considered topic in this study. This topic has been studied for the longest time, and the major idea of this topic is to regularize important weights for previous tasks to overcome the catastrophic forgetting. And this figure shows the simple geometric interpretation of regularization-based continual learning. Each ellipsoid denotes the space of weights that has a low error for each task, when our model is located in zeta A star. The naive approach using fine-tuning will make a model locate in the region only for a low error for task B, as shown in this blue line. It means it causes catastrophic forgetting for previous tasks. To overcome this problem, several regularization-based methods propose a novel idea to make a model located in the intersection region of ellipsoids. For example, like a red line. The general form of the regularization-based continual learning is denoted as this equation. For the training time t, cross-entropy loss function for the task t is minimized. At the same time, regularization for the current model is also applied. Zeta I denotes a weight of the current model, and the zeta t minus I denotes a weight of the model trained until the previous task, and I denotes each weight point. The regularization-based method gives a L2 regularization to the current model using the set of estimates of the weight importance, omega. And lambda is a hyperparameter to be tuned. In short, where estimating the weight importance is most important in the regularization-based method, so several papers propose a different way to estimate it. In this point, my research motivation starts from the question when there is no intersection region between tasks, how we overcome the catastrophe forgetting on the previous task. Let's see this figure. We can think that someday of continual learning, the intersection region may no longer exist. For example, the case of learning the third task in this figure, and in this case, the regularization-based method highly depends on the hyperparameter lambda. It means if we set a strong regularization, the model will be located in the region for the previous task only. As a result, stability of the model will be high, but plasticity is not. Reversely, if we set a weak regularization strength, the model will be located in the region for the future task. And it means the model will suffer from catastrophe forgetting for the first task. In short, the trade-off between stability of plasticity of the regularization-based method is inevitably affected by the hyperparameter strength, even if we well estimate the weight's importance very well. To overcome this limitation, in this work, we propose to apply the concept of wide local minima. Before introducing the core idea, I will briefly explain it. Wide local minima denotes that the local minima where the loss does not change significantly according to the change in weights. The concept of wide local minima has been considered one of the most important topics in the generalization of neural networks. As shown in this figure, many of us find out that even if neural net is non-convex, wide local minima exists, and if the model converts to the wide local minima, it can have a better generalization than a model located in a sharper minima. So let's back to the previous geometric interpretation. Our core idea of CPR is simply applying the concept of wide local minima during the regularization-based continual learning. It means if our model converts to the wide local minima at each task, we can interpret it as that the weight ellipsoid for each task becomes larger than before. As a result, the intersection region can be also larger than before, making the method less sensitive to the hyperparameter, so it can increase both the plasticity and stability at the same time. In order to implement the idea, we propose a simple combined regularization for regularization-based continual learning. It means in this general form of the regularization-based continual learning, we simply add entropy maximization, which is KL divergence between the model's softmax output and uniform distribution. The reason that we select entropy maximization is that the author of the paper experimentally demonstrate that adding entropy maximization makes the model converge to the wider local minima than before. Also note that CPR is not applicable to CPR is not just for a single regularization-based method. So CPR can be generally applied to any kinds of regularization-based continual learning method. So now we should have to check in experiments in that first, does CPR really make it converge to the wide local minima? For this, we trained the model in the scenarios of continual learning with SciPy 100 dataset dividing into 10 tasks. We used EWC, which is one of the famous regularization-based methods, and trained 2 models with and without CPR. Also, to check the loss landscape of neural networks, we use PySEAN, which is open source library and provides a function to plot the estimated loss landscape by approximating the Hessian of neural networks. Experimental results shown in this figure, and we generally observe that after applying CPR, which is the red color, the loss landscape become flattened than before. Another method to directly check whether a model converges to what the wide local minima is plotting the changes of loss after perturbing weights. We conducted experiments with the same models used in the previous experiments, and the results are shown in this figure. X-axis denotes the level of variance, and Y-axis denotes training loss. We add Gaussian noise with several variants to the weights of the model. And we plot the training loss of it. We again observe that the model trained with CPR is much less sensitive to adding noise to the weights, demonstrating the convergence to the wide local minima. Our next step is we have to check that the CPR really increase plasticity and stability in continual learning. To check this one, so we implement EWC algorithm again, and we add our CPR term with different hyperparameters. And blue line means the average accuracy, which is a generally used metric for continual learning. And yellow one is forgetting measure, which is measure for stability. And red one is the intransigence measure, which is a measure for plasticity. From this experiment, we observed that the original EWC, applying CPR to EWC always get a better result than original EWC, even though we naively chose the hyperparameter better. So this result again show that CPR can increase not only increase the plasticity and stability. So as a result, CPR can increase the performance of continual learning algorithms. So now we have checked that CPR, the effectiveness of CPR. So we have tried to apply, show the effectiveness of CPR in various experimental settings. For this, we experiment with 4 benchmark data sets and 5 SOTA regularization-based methods, which is EWC, SI, MAS, RWORK, and AGSCL. And as I told before, so we use 3 different metrics: average accuracy and measure of stability, forgetting measure, and inference measure, which is measure of plasticity. Table is quite messy, but in short, we observed that applying CPR increased the plasticity and stability in all cases. As a result, performance of each method increases. And this is a result of plotting result of before results. So we can observe that after applying CPR, which is bold line, we can observe that CPR can increase the all accuracy in all task steps and all data sets such as SciPy 100, OmniGlot, and COP 200 data set. Another additional question is, can CPR be only applied to the regularization-based method? We could conceptually imagine that the concept of wide local minima might be helpful to another types of continual learning method. To check it, we experiment with other types of method, including parameter isolation method and replay method. As a result, we observed that converging to the wide local minima is also helpful to other types of continual learning methods. Finally, our CPR is not restrict to the classification test. So we conducted an experiment of continual reinforcement learning scenario. For this experiment, we trained an agent using PGD algorithm. 8 Atari tasks are continually trained with each regularization-based method with or with CPR. As a result, this figure again shows that for all tasks, at the all tasks, our CPR can increase the accumulated performance. It means that our CPR is also good for the continual reinforcement learning setting. This is the final slide. So in this topic, I propose a really simple idea, which is CPR. As a result, we can observe that we make a double connection between wide local minima of neural networks and regularization-based continual methods. As a result, we conducted many kinds of experiments. We observed that our method can be applied many kinds of continual learning scenarios and also supervised continual learning scenarios and reinforcement learning setting. And also in our paper, we gave us some simple theoretical interpretation in terms of information projection. And then this is the end of my talk. Thank you for attention.